Welcome to the lecture on distributed minimum spanning trees and distributed snapshots. So what we had seen in the earlier lecture on leader election, that if we are able to somehow overlay a tree on top of a network, on top of distributed nodes, if we can somehow overlay a tree instead of a ring, which we have been traditionally used to be doing, so then what we can do is many distributed algorithms become simpler. For example, electing a leader, finding the smallest element, minimum finding, all of that becomes much easier. So in this lecture as well, we will discuss one way of taking a snapshot of a network. That also becomes easier if we have a tree. So which tree should we choose? Well, a good tree is a minimum spanning tree. The reason being, it minimizes the length of the edges, so it kind of keeps things close by. So we will discuss the Gallagher-Hamlet-Spira algorithm, the GHS algorithm. We will discuss the overview, the algorithm and the analysis, and then everything about distributed snapshots. So let's first look at some basic properties of an MST. So it is important that before the MST is understood, the following algorithms, the Kruskal's algorithm and the Prim's algorithm, both of these are understood quite thoroughly, including the proofs. It is very important to go through both of these algorithms, the Prim's algorithm and the Kruskal's algorithm for sequential MST finding, and the proof of the Prim's algorithm particularly is very important. So the inductive proof of the Prim's algorithm, you should go through it. Alright. So now I will suggest a few, so I have already suggested algorithms, but you can look at it from a popular text on algorithms first, and the proofs are important. So now without going into the depth, I will list a few properties of an MST that we shall use. The first is the property of uniqueness, which says that if each edge of the graph has a unique weight, then the MST is unique. Alright. So this goes without saying, this is easy to prove. So this is our first point, that if each edge of the graph is unique, then the MST on a whole is unique. Okay. So you will not have two MSTs. Of course, if you have weights with if you have edges with same weights, then you could have a non-unique MST, in the sense two MSTs with the same weight. Otherwise, it will not happen. Furthermore, here is one more theorem that is a direct outcrop of the proof of the Prim's algorithm, which says that it's called construction based on the least weight edge. So let's consider a fragment as a subtree of a MST. So if we take a minimum spanning tree, so let's say that this is the tree, right? So let us take a subtree of the minimum spanning tree and let's call this a fragment. Okay. So let's refer to this as a fragment. So then an outgoing edge of a fragment has one endpoint in the fragment and one node outside the fragment. As you can see over here, this is the outgoing edge. So this has one node within the fragment and one node outside the fragment. Alright. So we basically have a subtree. Then we have the rest of the tree over here. And there is one edge that connects this fragment with the rest of the tree. And so basically we now are looking at some property of this edge. So for anybody who knows the proof of the Prim's algorithm, this theorem will be rather obvious, that if F is a fragment and E is the least weight outgoing edge, then F union E is also a fragment. What does this mean? That F is a fragment and this is the edge E. So if I consider this to be the fragment and this to be the rest of the world, and then I draw a line over here, so there might be multiple edges that go from an edge of the fragment to the rest of the tree. So this could be one edge, this could be one more, this could be one more. So let them be E E dash and E double dash. So what the theorem is saying, just look at it. If E is the least weight outgoing edge, which means that out of all the edges that connect this fragment to the rest of the tree, if E is the one which has the least weight, then the claim is that F union E, which basically means that I can create a new fragment like this, and this will also be a fragment of the MST in the sense that E will be an edge which is a part of the MST. That makes F union E also a fragment of the tree. So this of course is easy to prove. So let us look at this once again. So let's say that this is a subtree, this is a fragment, and you have one edge E to the rest of the nodes. Alright. And so then currently it's a tree, we claim that this is the MST. Let's assume this is not the case. Well, if this is not the case, then what would happen? Then it would mean that there is some other edge E dash which is a part of the MST and E is not a part of it. Well, but what you would see is that if let's say now I add E dash, this will clearly create a cycle. In this cycle, we know that the weight of E dash is greater than the weight of E, right? And let's say within this, if let's say I remove E, we are claiming that this is the MST, but I claim that there is a contradiction. The reason is that if I add edge E, okay, so let's assume that the rest of the tree remains the same and its weight is fixed. So then if I add edge E, let's maybe say that the weight of the fragment is WF and the weight of the rest is WR. So let us consider two trees, one that has E and one that has E dash. So the tree that has E, its weight is WF plus the weight of E plus the weight of the rest of the components, the rest of the tree. And the tree that has E dash, its weight will be again the weight of the fragment plus its own weight, because at that point edge E will not be there, plus the weight of the rest of the tree. So clearly these parts are common, and we claim that this is the MST, but this cannot be the case, because for this to happen, W E dash has to be less than the weight of E, which we clearly know is not correct, because W E dash is greater than, right? And so we clearly know that this is not correct. Hence, any out of all the outgoing edges, the least weight outgoing edge, which is edge E in this case, has to be a part of the MST, and F union E will thus become a fragment. So this is exactly the intuition that is used in the Prim's algorithm to iteratively, or I should say recursively, increase the size of the tree. So what we do is we first consider the starting node as a single node, then we look at all of its neighbors, pick the least weight edge. So this becomes a new fragment. Then again we draw another boundary around it. Then we pick the least weight edge. Again we draw another boundary around it. Again we pick the least weight edge. Maybe this is the one. So we gradually keep on expanding the boundary and we keep on adding edges. But our criterion always is that for the boundary around the fragment that we have created, we just pick the least weight edges and we just keep on adding them. And given the fact that we have proved this theorem now, that F union E, maybe I'll write it in a slightly better form. F union E is a fragment, right? We are always sure that the edge that we are adding is a part of the MST. So if we continue to grow the tree, ultimately we will encompass all the nodes, and any n node tree will have n-1 edges. So when we have n- edges, we will know we are done. And the proof is by induction. Given the fact that at every step we start from an MST for that fragment, and adding a new edge still maintains the MST property, we can prove that when we reach the end, which is when we cover all the n vertices with n-1 edges, the tree continues to remain an MST. Of course, if you are not able to understand what I said, then I would suggest that you don't go forward, because you will not be able to understand the rest. You first take a look at the proof of the Prim's algorithm. Okay. Okay, that's the most important. So you first take a look at the proof and then you try to understand this theorem over here. If this theorem is understood, then only you proceed, otherwise you don't. So the overview of GHS is like this, that you want to take Prim's algorithm and create a distributed version of it. So initially each node is a fragment. So initially every single node is a fragment. Gradually what happens is nodes fuse together to make larger and larger and larger fragments. Something that we also saw in ring-based leader election, where the windows kind of grow larger, larger, larger and larger. So in this case, the fragments fuse together to make larger and larger fragments. And a fragment, of course, joins another fragment via the previous theorem, which is this theorem, which is by identifying the least weight outgoing edge. Furthermore, how to find the least weight outgoing edge? Well, all the nodes within a fragment run a distributed algorithm to find the least weight outgoing edge. Gradually what happens is that the number of fragments, this number itself decreases. Ultimately only one fragment remains which covers the entire set of nodes, and of course in this case we are assuming that the graph is connected, right? And in this case, and then that is the MST. Alright, so one assumption we make is that of course we have unique edge weights. That gives us a unique MST. That is one. And the other is that the graph is connected. Okay, so these are the two assumptions, but this assumption is made by other algorithms as well. Nothing special over here. So what are the properties of a fragment? Okay, so now we are getting into our distributed algorithm, not completely, but we are kind of looking at it from the outside. So let us give each fragment a unique name, a unique ID. So when two fragments combine, then all the nodes in one fragment will change their name to a new name. Alright. So what you see is that if two fragments are combining to create a bigger fragment, then of course a new name has to be assigned. The same way the two companies merge, right? So what happens is that typically if a large company gobbles up a small company, then no name is changed. But if two equal size companies kind of merge, then the name kind of reflects both. We will see something similar happening with fragments. That assume that fragment F1 is combining with fragment F2. We will say it can only do so if level of F1 is less than equal to level of F2. What this means is that if one fragment F1 is joining fragment F2, it can only do that if F1 is the smaller guy, is smaller or is equal. Okay, but so which basically means a bigger fragment cannot gobble up a smaller one, but a smaller one can always approach a bigger one or one of same size, asking it to join. Fine, fair enough. If level of F1 is less than level of F2, so level is somehow indicative of its size. We will see how. If level of F1 is less than level of F2, then all the nodes in F1 take on the name and level of F2. So which basically means if a smaller company joins a big company like a multinational, then all the nodes in the smaller company F1 will take on both the name and the level. So every fragment has a name and a level, and the level is somewhat indicative of its size. So if level F1 is less than that, then F1 loses its identity. So then the nodes of F1 will take on the names and levels of nodes in F2. If however, there's an important point to keep in mind, if however, level F1 is equal to level F2, then the level of both the fragments gets incremented by 1. So this is important, that if two fragments with an equal level are merging, then what happens is that the level of the combined fragment increases by 1, gets incremented by 1. That's how the level increases. Furthermore, we will see what happens to the name. So that is also interesting. They get a new name And the new name is basically something that kind of combines the names of both. So we will see in a couple of slides how that happens. But pretty much if the levels are equal, it's more complicated than when the levels are not equal. The nodes of F1 union F2 get assigned to a higher level, which is the old level plus plus. Alright, so what we are saying is that look, we have a small fragment, we have a big one, and we are combining them. The combining edge is EF. So if let's say F1 is less than F2 in terms of levels, then of course the name and level of F2 gets transferred over here. But if they have the same level, then the level for both is incremented and a new name is given to both, such that it becomes one big homogeneous fragment. Alright, so we will now define two important combining rules and one weighting rule. So let F1 L1, F1 is fragment F1 with level L1, be desirous of combining with F2 L2, where E F1 is the least weight outgoing edge of F1 and it terminates in F2. So between F1 and F2, E F1 is the least weight outgoing edge from F1. So in consonance with what we have said, there are two combining rules. One is the less than rule, LT rule. If L1 is less than N2, then we combine the fragments. All the nodes in the new fragment will have name F2 and level F2. It's like the smaller guy merging with the bigger one, which we have discussed in this slide as well. Alright, if L1 is less than N2, that's what we do. That nodes in the new fragment will have the name F2 and the level L2. But if they are equal, that's where we said that there is a catch. If the levels are equal, then we check if their least weight outgoing edges are the same or not. Okay, so this is the catch over here. So in this case, we will combine when we have the same levels, subject to the fact that our outgoing edges are the same. If they are not, we will not. So the two fragments combine with all the nodes subject to this. So then it's important, even if their levels are equal, they just don't combine like that. Only the LT rule, if the levels are not equal, then only L1 will combine with L2. Otherwise, we will see that their outgoing edges have to be the same, least weight outgoing edges. Only then we combine, and then as we have discussed, the final level is L1 plus 1. And we also discussed that we'll give both the nodes, we'll give both the fragments and the nodes within them a new common name. And the new common name is basically the name of the edge. So let's assume that every edge has a unique weight and unique name also. And the name could be just a combination of the two node IDs of the edge, right? So it could be that, doesn't matter howsoever the name is derived, but we will essentially, the edge will be the common name for the nodes of both the fragments F1 union F2. Okay, and if any of these above rules don't apply, we just wait, right? We wait for them to apply. So this is basically telling us that what we are doing is that small fragments will always go and merge with bigger ones, but equal size fragments will have a key condition, which is that their least weight outgoing edges need to be the same. Only then they will actually merge. So they will increment their level and the new name will be equal to the edge that connects them, the least weight outgoing edge. So now we will discuss our algorithm. It's a fairly long algorithm, so we will have to discuss the state that we maintain. So we have three states: sleep, find and found. Sleep means the node has not been initialized. Find means the node is currently helping its fragment search for EF. EF is the least weight outgoing edge. Found means EF has been found or the least weight outgoing edge has been found. So that is what this means. Alright. So here also I am P and the other node is Q. So every node maintains an array called status queue. So status queue is basically the status of the edge from P to Q. So status queue, where I am P and other nodes are Q. So for every Q which is my neighbor, I'll have a status array with a Qth entry. So then it will have three values: basic, branch and reject. Basic means that the edge is unused. Branch means the edge is a part of the MST. Reject means the edge is definitely not a part of the MST. Basic, branch and reject. Basic means as of now we don't know its status. Branch means we know its status and we know it's a part of the MST. Reject means we know its status and we know for sure that it's not a part of the MST. Then we have discussed name and level, right? Name of the fragment, level of the fragment. Parent. So the parent basically says the following, that let us say two nodes with the same level combine, or let's say even a smaller node combines with a bigger node. So there will always be a combining edge. So let us consider first combination with the LT rule. So let's say that this is a small fragment and this is a much bigger fragment. So in this case, right, if this is a much bigger fragment, every node over here will basically point to some other node which points to some other node, which will ultimately take it towards the combining edge. So every node will point towards the combining edge. So these are essentially parent pointers which take us towards what is called the combining edge. And similarly, if we have a combination of two fragments where the level was the same, so every node here will also have parent pointers towards this combining edge, the common combining edge. And every node here also will have a parent pointer that goes towards the common combining edge. So we will see why this is the case. But this is how the parent pointers actually work. And then of course we have a bunch of temporary variables like best weight, best node, test node and so on, which are purely, temporary variables. Alright, so now let us discuss the algorithms. So the algorithm, so we have many algorithms, 8 or 9. So always the assumption is that the current node is P and the neighbor is Q. So let us look at the initialization. So let's say that initialization is when things are starting. So let's say that I am node P. And from node P, PQ is the least weight branch. Fair enough. So clearly, if this is the initiator, I can draw a circle around it. PQ intersects this circle. And this, needless to say, is the least weight edge. So I set the status of this edge as a branch, status Q as branch. I start from level 0 and my state is found. I found the least weight edge. Rec 0 means, we will see what rec means, but at the moment for this case it is 0. And I send a connect message to Q. So the P will send a connect message to Q. Okay. And so this is when I'm initializing. So this is when I'm starting. I know that the level of Q will at least be my level, or we will see essentially as far as it is a least weight edge. Let me send a connect message and let's see what Q does. If Q responds, I connect, otherwise I don't. So what I send is I send a connect 0 message. We'll see in a second what the 0 stands for. But essentially, as far as I am concerned, if Q is my least weight edge, I request Q to kindly connect with me. And I do that by sending a connect message. Alright. And you can clearly see that in this case, PQ will be a branch. Right? Will be a branch of the MST. So there is no reason why it should not be. Now coming to algorithm 2, which is the processing of the connect message. So when I receive the connect message, the message type is connect and L is the level of the sender. So in this case, the level of the sender is 0. So when a node receives a connect message, of course you can say P sent it to Q, but what is our convention? Our convention is that I am always node P and the other node is Q. So as far as I am concerned, I am node P. I am getting a connect message from another node which is Q. So this is the convention that we adopt. Might be confusing, but this is what we do. So now what I do is that, look, I have gotten a connect message. So I will look at my level and the level of the connector. So if L is less than level, which means that the level that is coming along with the message, if that is less than my level, no problem. This means that a smaller fragment wants to combine with a larger fragment. So I can happily combine with the rule LT. So absolutely no issues. So I'll set the status Q to branch, right? And then I will send an initiate message to the smaller fragment. This is a large fragment. I'll send an initiate message to the smaller fragment saying that, look, I have accepted your connect message. You, as of now, you are initiated. This is your new level. This is your new name. This is your new state. And the state is whatever is my state. If currently I am searching for my least weight edge, now you are a fragment and you join me, so you need to help me, right? So whatever is my state, that is currently your state, so you take it and you initialize yourself. No problem, so this is sent to Q. So just a quick disclaimer before this point, this P and Q business can be confusing. Because you will argue that, look, in the previous slide, P sent a connect message to Q. Now you are saying that I am P and I received a connect message from Q. How is this possible? Well, in a distributed algorithm, we are looking at distributed state machines where every node is an independent computing entity. Okay, this is a node. It gets a message. Based on that, it updates its state tables and then it sends messages to other nodes, including the one that sent the message to it. So that's the reason when distributed algorithms are written, this might sound tricky and confusing, but I am always node P, whoever is doing the action, and whoever is sending or receiving a message, the entire world outside, is always node Q. So this of course is complicated, but if you can appreciate this complexity, then appreciating such algorithms will become much easier. So let us come back to our discussion. I'll clean the slide. So the idea here was that I'm combining with rule LT primarily because here I have a case where I have a small fragment that is requesting a bigger fragment to connect, and the bigger fragment has no issues at all. So it sets status Q to branch and sends an initiate message back to the smaller fragment saying that, okay, look, this is my name, level and state. Henceforth, this is your name, level and state as well. Else if this condition is not holding and the status of the node is basic. So we will see, so the status of the node basically has not been, as far as I am concerned, this node has not been explored, so the status is basic, right? So then what I will do is I will combine with rule EQ. So why will rule EQ be useful over here? And why not, so we are automatically saying that if the status of the node is basic, does this automatically mean that L is greater than level, right? And do the conditions for rule EQ actually hold? Well, so you will see that they actually hold, and so you will see that they actually hold, and there is no error over here. But it is important to remember this. We might come back to this point. So what we do is that we combine with rule EQ. So for this we send the initiate message, right? So why EQ will come here is at the moment a leap of faith, but we'll break that. So we send an initiate message. So we are saying that they are at the same level. So well, no problem. So your new level is level plus 1. And your new name is the edge via which this message is coming, the joining edge, which is PQ, right? So P on one side and Q on the other side, and that this is how we are joining. And so the name of the edge is PQ. And furthermore, given that we have joined, our new state should be equal to find. Find basically because now we have become a bigger fragment, so we further need to expand our fragment, which means that we need to find our least weight outgoing edge and grow. So your state is find as well as my state also has to become find. So this is basically what we do, that we send an initiate message to the new fragment, and the new fragment starts the process of finding. Alright, so we did make certain assumptions here, we have not proven, but let's continue. So the application of rule LT and rule EQ would be very clear over here. If you want, you can just go back to this slide where we defined the EQ and LT rules, and as you can see, it was not all that complicated. So here we basically, LT was a smaller fragment with a larger fragment, and EQ was both the fragments are the same size and they have the same least weight outgoing edge. So the question that we have kept open is, why will the rule EQ be useful over here, which we will gradually see why. Now how do you process the initiate message? So let's say that again node P, it's always node P, gets an initiate message from node Q, I'm sorry. So the message type is initiate. We get a level dash, name dash and state dash. So we set the state, no problem. We set our level name and state to level dash, name dash and state dash. So my level is now level dash, my name is name dash and state is state dash. Furthermore, given the fact that this is the combining edge, I set my parent equal to Q. Okay. So if this is PQ, I set my parent equal to Q. Then what I do is I propagate the update. So I define a few local variables, best node, best weight and test node. We'll see what these are. So for each of my neighbors, for each R element of neighbor P, so basically for each of my neighbors, as long as the status is equal to branch. So essentially I propagate this along the small MST that I have created. Alright. So along the small little MST within my fragment, I forward this message, which means that the status has to be branch. This means that it is part of this MST fragment. And furthermore, R is not equal to Q, which means that I don't send a message back to my parent. I only send it to my children. So this indicates that I'm only sending the message to my children. And I'm sending the initiate message, which means that look, now your fragment has combined with some other fragment. So now we are under the rule of a new fragment, or let's say we all have changed our name and level. So I have already done that, now you do it. So that's the reason we just send an initiate message with a new level name and state to, let's say, a child R. No problem. The child R also does the same thing. So on and so forth. So what you can clearly see is that all of them ultimately end up pointing, indirectly of course, towards the combining edge. Indirectly means via parents. No problem. Now what we do is, we see what is the state. If the state is equal to find, then it means that I am supposed to play my job as a good member of a fragment by finding the least weight outgoing edge. So I set the rec variable to 0, again an internal state variable, and I call the function findMin such that we all members of the new fragment can find the least weight outgoing edge. No problem, findMin. FindMin is not hard at all. So my findMin, by the way, is not a message, as you can see. It is an internal function. So the internal function is being called over here, findMin. FindMin, this is what it says. So again, I am P, the other node is Q. As long as there is some node Q which is an element of neighbor P, which means as I look at all the neighbors of P, as long as there is some Q which is a neighbor, such that status Q is equal to basic, which means that this, as far as P is concerned, is an unexplored edge, and out of all of its outgoing edges, right? So out of all of its outgoing edges that are basic, WPQ is minimal, which means that out of all of its candidate outgoing edges, so clearly if the status of an edge is branch or reject, it cannot be a candidate outgoing edge, right? It can only be a candidate outgoing edge if its status is basic, which means it is unexplored. So if it is unexplored, out of all of them, I find the node Q such that PQ out of this set is minimal. No problem. Then I say that Q is a test node. So then I try to check if it is possible to add Q to my fragment, alright, and kind of grow the fragment via this PQ edge. So what has happened? So what has happened is that, look, two fragments are merged. There has been a common merging edge. Then initiate messages have been sent. So now let's say every node in at least the new fragment is aware that its boss has changed. If let's say the boss was in the find state, then all the nodes in the joint fragment will also be in the find state. So boss means the larger fragment. If both the fragments are the same level, then what we will see, in a few future algorithms, this is algorithm 4 in like algorithm 6, 7, 8, 9, is that if they are the same level, both of them will actually send initiate messages to each other, and then they will increment the levels in both the fragments, and then they will also shift to the find state, which means that they will start to find the least weight outgoing edge. So every node will try to do its part. So every node, what it will do is it will scan all of its basic edges, neighbors, whose status is basic, find the minimum one, and try to see if a connection can be initiated with it. So it'll do a test. So it will send a test message indicating its level and its name. So name, of course, is the name of the fragment, right? Not its name, the name of the fragment that it belongs to test node. Test node in this case is Q. If of course such a Q is not found, then it will send test node to null and report this fact that look, I didn't find anything. Alright. So now there are two possible outcomes of find min. One is that you send a test message. The other is that you report that look, I didn't find anybody. So let us see what happens to both. So how did we reach here? The big picture is that look, after fragments merged, you cannot stop the process of merging, right? So you can't stop the process of a fragment growing. So after you have merged two fragments, it is a job of every single node in the merged fragment to look for further expansion. That is where we enter the find state. In the find state, every node needs to do its part, which means find all of its neighbors with a basic status, find the minimal weight neighbor in this set, and see if a connection with it can be initiated by sending a test message. If it doesn't find, of course, it should report. Fine. So receiving a test message. Again, same convention. I am node P. I receive a test message from node Q. So this PQ stuff can be quite confusing. In fact, the first time that I read it, I thought it was pretty challenging. But that said and done, now I've gotten used to it. You also will be. So this is basically that I am getting a test message, I am P, from Q, and level dash and name dash is Q's name and level. So if Q's level is greater than my level, then by the EQ and LT rules anyway it can't combine with me. So we just wait. I just keep the message in an internal buffer and I don't do anything. I just sleep on it. Else if name is equal to name dash, which means my name and Q's name is the same, which basically means that a message has been sent to another node of the same fragment. Well, Then if the status is basic, what I do is I mark the status to be reject. So this clearly cannot be an MST, because you cannot have an edge to a node in the same fragment. That's not allowed. That will create a cycle in the tree. So we know for sure that, look, this cannot be a valid tree edge. So then what do? This has to be a reject. Alright. We need to reject this edge because it's to an internal node. So I just reject it. No problem. Then let's say that if Q is not equal to test node, which means that as far as I am concerned, I might have sent a test message to Q and I would have set test node. So just look at this, I'm clearing off the ink. So whenever I send a test message to some other node, I set that node to the test node as the test node. See, if Q is not the test node, which means that I have not sent a message to Q, right? Saying that, would you want to join me, because the status of this edge was unexplored. Then clearly a reject message needs to be sent to Q telling it that, look, we can't join because we are actually a part of the same fragment. Alright. But if let's say Q is equal to test node, which means that already a test message has been sent, then I should call findMin again and then move to some other node, because clearly Q is not the candidate. And Q will also mark this edge to me as a rejected edge because it would get my test message. So recall that when is the test node set? It is set when a test message is sent. So the fact that Q is a test node, it basically means that a test message, which is this case, so this is not equal to and this is equal to. So in this case, the fact that Q is a test node basically means that a test message has been sent to Q, which means that over due course of time, Q will mark the edge to me as reject, so I need not bother. As far as we are concerned, I know that Q is a part of my fragment. Q knows that I am a part of his fragment. We mutually know each other if it is this case. If we mutually don't know that, I should make Q explicitly aware of the fact that, look, Q, you should not have sent me a test message in the first place because you and me are a part of the same fragment, so we can never have a connecting edge between us. Hence, I am rejecting this message. So as I said, regardless of how the message is sent, either as a test message or as a reject, Q will ultimately get to know that it is a part of the same fragment as P, which is myself, and it will pretty much mark me as invalid. So given the fact that Q is now a rejected node, right, what I need to do is I need to again call findMin. And if I again call findMin, what would happen is that in this case, the status of Q will not be basic anymore. The status of, the other Q, the Q that we have been talking about in this slide. Again, P and Q is slightly confusing, but the good thing about a video is that the same slide can be seen over and over again to get the basic idea. So in this case, since the status of Q is equal to basic, this thing doesn't hold anymore because we just rejected it. Then some other node has to be picked out of this set. So we'll have a new minimum. Again we do the same. Again we send a new test message to the new minimum. If it happens to be in my fragment, so which means that I am a part of this fragment, I send a message to Q. If somehow Q also happens to be a part of my fragment, unbeknownst to me, either it would have sent me a test message, so with that I will get to know that Q is actually a part of my fragment, so I'll mark it as invalid, or Q will send me a reject message and then I'll mark it as invalid, and again I'll come to this point where I will start testing with some other neighbor of mine, that satisfies this criteria, and if I don't find a neighbor, I will report this fact. Alright, so now let me clean off the ink over here. So the key point is that, of course, if this holds, that Q was a higher level, I wait. Otherwise, we are part of the same fragment, then of course, essentially what I do is I reject Q. Right, the branch is rejected, and I call find min again because I would like to explore some other neighbor of mine. No problem. Otherwise, if the names are unequal, names are not the same, if the names are not the same, then what I do is I send an accept message to Q, because there is no reason why I should not. Alright, so there is absolutely no reason why I should not, and the thing is that number one, there is no issue with the less than or equality, and furthermore it is the least weight edge between the two fragments. Okay, so after I receive an accept message from Q, which means that Q does not have an objection, I set, so once let's say P gets an accept message from Q, which means that Q does not have an objection, then I set the test node to null, and let's say if the weight of PQ is less than the best weight that I have seen, then I set the best weight to weight of PQ, and I set my best node to Q, and I report this fact. So what I report is that, look, I have found something, and as far as I am concerned, my best neighbor is Q, and report, mind you, is not a message to another node, it's just a function call. Right, so it's just an internal function call. It is not a message, and the internal function call will be able to see these internal variables. If I receive and also what do I do if I receive a reject from Q? Well, then I change the status of the edge from basic to reject, and I continue with other neighbors. So no problem. What is the idea? The idea is that, look, my state is find, so my job is to find neighbors. I start contacting my neighbors. In an ascending order, first I look at only the basic edges, not branch or reject edges. And in an ascending order of weight, I start contacting them. Either they can just hang on to my message and not reply to me. Right? So that is one option that they have. The other is that they can either accept or reject. If they accept it, I record this fact. If they reject it, I move on to some other neighbor of mine. If let's say this rejects, I move on to another neighbor of mine. So what does the report method do? It's a method, okay? It's not a message, it's a method. So what the report method does is that number one, it looks at this set. So this is the set of all Q. So again, I am P and the other node is Q. Any other node is Q. So I look at all my neighbors such that the status of the neighbor is branch and it is not a parent. So it means it's a child. Right? So both of these things together, it means that the other node Q is a child because it's a neighbor of mine and it's not a parent. So it can only be a child. And if rec is equal to this, so basically this expression over here, the cardinality of this set is essentially the number of children. So if rec is equal to the number of children, which basically means that similar, if you go back to the leader election algorithm, in that we had discussed leader election in trees where all the children send their values to their parent and then it kind of propagates up the tree. So this is basically saying that, look, if I have received a message from all my children and a test node is null, so when do I set the test node to null? When I receive an accept message or when I find that none of my neighbors fit the criteria, which basically means that no outstanding test message is there. So let's just look at the test node thing. When I receive an accept, I set it to null. Alright. And when else do I set it to null? I set it to null when I run out of neighbors. So then also I set it to null. Otherwise, I don't set it to null. If I have sent a test message and it is outstanding, then it is non-null. So the fact that here I am saying that test node is equal to null, which basically means I have finished my job of testing. So what it means, if you go back to the tree-based leader election algorithm that was in the previous lecture of the slide set. So we had said that every parent essentially finds its own minimum and also aggregates all the minima sent by its children. Once it is done, once all of his children have sent a message, which is precisely being captured by this complicated looking mathematical formula over here, which just simply put means that all my children have responded to me, and test node is equal to null, which again in simple layman's terms means that I am done with my job. So together the if statement means that my children are done with their job and I am done with my job. I set the state to found and I report as an honest child to my parent that look, I am sending you the report message. This is the best weight edge that I found. The best weight edge means, as far as I am concerned, for my subtree, this is the least weight outgoing edge. It's a valid least weight outgoing edge, and furthermore, the node on the other side agrees to connect with me. So I have a upfront commitment from the other node that is not going to refuse. So then how do I process the report message? So when I get a report message from Q, so again I am P, I am always P, and I get a report message from Q. In this case, Q is my child. So then similar to again the last slide of the leader election algorithm with trees, we said that a parent is its own parent and own child. So something similar to this is happening over here. See, if Q is not the parent, in the sense if my child is not my parent, which of course holds for the root node, if let's say omega here is less than the best weight that I have seen, then the best weight is omega and the best node is Q, it means that as far as I am concerned, the child that is sending me the best weight is the best node, so I will record this fact. And furthermore, given that my child is sending me a message, I will just set rec equal to rec plus 1, which means that one of my children has responded. And then I will call the report function. The report function is the same as this, which given the fact that we have understood this, I can clean off the ink, right? And so this will basically see, in this case, we will check whether all my children have replied or not, and given the fact that the rec variable I just incremented. So I'm assuming that all of these variables are global within the scope of a node. So since I have just incremented this, it is possible that the if condition becomes positive and I enter this. If I don't, then there is no problem. I just come back and I just keep waiting. So this part of the code basically means that every parent waits for all of its children to report their best edges that they are finding. It computes the overall minimum, reports that to its parent. So this is, as I said, what would happen in any tree, that every subtree will report its best. Again, the parent will collect everything from its children, which again is the root of its own subtree. And it will just propagate that up and up. No problem. Until you reach the root. What is the root? So the root in this case is slightly complicated. We will come to it. So otherwise, if Q is equal to parent, in the sense I am receiving a message from my parent, which means my parent is sending me the report message. It's kind of strange, but we'll see when that happens. So then we will see. So in this case, Q is equal to parent. If the state is fine, okay, if my state is fine, I'm still finding, then I wait. if omega, what my parent is reporting, is greater than best weight, which means that my best weight is actually the best, okay, then I change the route. Otherwise, if let's say omega is equal to best weight, which means me and my parent both are reporting infinity, this means that we have actually reached the end. There are no eligible edges. So then the MST condition has been met and it's all done and terminate. So now the structure of the parent is quite important, okay. And so if you go back to the connect message, so then the parent thing is quite important, but I would like to discuss change route first before going to parent because they are connected. So let us now discuss the last algorithm, which is the change route method. So here what happens is that we have found out in the entire fragment which node is connected to the least weight edge. So this has been found out. Why and how? Well, so basically every single node of the subtree broadcasted its best values to the root, and finally the root computed the minimum operation over here, as you can see, and updated the best weight and best node. So best node is of course one of its child nodes that has a path to the eventual best node which lies at the edge of its fragment, right? So every node just keeps a pointer to its child, and just by passing these child pointers you ultimately reach the edge where you have the edge that is the least weight edge of this entire fragment. So now when you decide to change your route, which basically means that you are basically rooted at this node that is at the edge. So what this essentially means is that if we consider all the nodes within this tree regardless of how they were, so this is of course similar to the Raymond's tree algorithm for mutual exclusion, which was there in our lecture set. So there what happens is we do a change route. So change route essentially means that every node updates its parent pointer to point to the new parent. So every node over here updates its pointer along the path, right, such that, so if let's say this was the old route, so all the nodes pointed to this, and the old route over here points to the new route which is over here, and this is of course the edge that is pointing to a different fragment. If this is F1, this is F2, and clearly via these edges it is possible to reach this node from any node within the fragment, because every node within the fragment in any case was pointing to the old route. So what will happen is that it will now, what we are doing is we are establishing a path from the old route to the new route just by flipping child parent pointers. So what we are doing is we start from the root, we just see the status of its best node. If it is a branch, then what we do is we send change route to best node. Alright, and no problem. And so we just keep on doing that. Ultimately what will happen is we will arrive over here. Then what will happen is that the status of the best along the core edge, what we will do is we will set the status of the best node to branch, in the sense at this point the status of the edge E from basic will turn into branch, which basically means that now we acknowledge the fact that E is the least weight outgoing edge out of the fragment, and furthermore we will send a connect message, connect level to best node, which means across the edge E to the other fragment. So what did we do? The summary is that in the entire fragment, each of the nodes looked at each of its children that are outside the fragment on undecided edges, started from the minimum, went up the ascending chain if there were any rejects, ultimately till the other side gave an acceptance that yes, I am willing to join. And then all of this information was sort of got coagulated all the way up to the root. and after that point a decision was made what genuinely is the best. Then subsequently another decision was sent back. Of course the parent pointers are flipped and I am not showing that in the slide, but then after that the parent pointers were flipped. So let's say that, let's say this edge over here was found to be the minimum. So then we set the status of this edge to be branch, and then we send a connect message, where the connect message will again take us back to algorithm 2. Where what was happening in algorithm 2? What was happening is that we were processing the connect message, and there of course if we found the LT condition we connected immediately. So here if you would recall, we had kept something open. So we had said if the LT condition is not holding, so what could happen? So if this is not holding, it means L is greater than equal to level, right? Which is fine. This means that from the outside a level is coming which is greater than equal to my level. So now what I do is that I look at the status of the edge. If the status of the edge is basic, then I wait, which means that, so what does this mean? This means that I have not made any decision about this edge, right? So even if I have sent a test message on this edge, I have technically not made a decision because I have not gotten any accept or reject, and so I have not made any decision, hence I wait. But let's see it is not basic. Then I come here, and this is where we had left a question open. What we had said is that what happens here? So what happens here now we know. So this basically means you reach over here, number 1 if L is greater than equal to level. Number 2, if the status of the edge is either accept, is either branch or reject. Okay. So let us look at the reject case first, that is easier to eliminate. See, if the status of this edge is reject, then there is no reason why a connect message should have been again sent by the same edge, because a connect message is contingent on the fact that an accept was received. But since a reject has been received, there is no chance that a connect message will be sent on the same edge, because it means that both the nodes are a part of the same fragment. So reject is not possible. So this means that the status of the node has to be branch, status of the edge has to be a branch, which means that from the point of view of both fragments, it is their least weight outgoing edge. Furthermore, L cannot be greater than level. This is not possible for a simple reason that for any connect to happen, it should have gotten an accept first. And if we actually look at it, if we just look at this line over here, whenever a test message is sent, in this case if L is greater than level, then it just waits. So then what would have happened is that in this case if L is greater than level, then no prior communication would have been initiated, in the sense an accept message would not have been sent. This means that this branch would not have been chosen, and definitely a connect message would not have been sent along this branch. So even L greater than level will not happen. So the only choice that we are left is that the status is a branch, and furthermore L is equal to level. Nothing else is possible. Given that nothing else is possible, what we see is that the EQ rule holds in this case. We were not able to see it the first time when we looked at this algorithm, but now we can clearly see that the EQ equality rule holds. The status of the edge is a branch, and furthermore the levels are equal, right? Because nothing else is possible, and that is how we initiate. So what would happen is, for two fragments at the same level, if we let's say take a look at their joining edge, so let's call these nodes P and P dash. I don't want to use P and Q anymore. So what would have happened is that P would have sent a connect message to P dash and gotten an initiate back, And P dash would have done exactly the same. Given that it's a branch for both, P dash would have sent a connect message to P and gotten an initiate back. And then what you see is in this thing that you send the parent, you set the parent to the other node. So you would have a parent relationship around this edge, which is also called the core edge, that would look something like this. So this is why I said that as far as all of these nodes are concerned, they will direct their parent pointers up here, but here you have the cyclicity around this core edge. So we can think of this edge as the parent and the two nodes here pointing to each other in a special kind of manner, and all the nodes within are pointing to basically the root, and both the roots are connected to each other in this fashion. Alright. So now what happens is that this becomes a bigger fragment. But let's say if this fragment now wants to join to another fragment, then what happens is that let us say that it finds a least weight outgoing edge. So the least weight outgoing edge can be over here. In this case, this cycle over here will break. Alright. So this cycle over here will break. So this edge will go away. And what will instead remain, if I want to draw it in a slightly bigger canvas, so what would essentially remain is something like this. If let's say these are the two fragments, initially what happened is if this is the core edge, this is how they were pointed towards each other. And if let's say this is the least weight outgoing edge, then this parent pointer will break down. Alright. And then a sequence of parent pointers will be used to come here. So this basically means that now, as you can see, all the nodes in this fragment are pointing here, as this is the new root. All the nodes of this fragment are also pointing here because they were pointing to the old root, so now they are pointing over here. Similarly, if this is joining with another fragment, depending upon the levels, depending upon what exactly is the level, you will have a connection that is made. Alright. And so let's say that this has a lower level than this, then of course this pointer is like this, and you will have a core edge somewhere within this fragment. Otherwise, this edge over here will become the core edge, and you will see such kind of a cyclic relationship. So this is kind of nice, interesting and elegant, yet complex. So what we have basically done now is that we have looked at these special cases, and we have furthermore said that what happens at the end. So what basically happens at the end is that we set the change root messages, and finally a change root happens, and so gradually that's the way that your fragment actually expands. Right, your smaller fragments keep joining around core edges, and they keep growing and growing. Ultimately, the entire graph becomes a single fragment. So now a little bit of an analysis. So we claim that there are order n log n fragment name or level changes total. We further claim that the message complexity is 2e plus 5n log n. E is the number of edges, n is the number of nodes. So what is the logic? Well, every node is rejected only once, correct? Can't be rejected more times. One test message and one reject message. So every node that is not a part of the tree, that is rejected only once, and that's it, finish. So this is limited to 2e messages. Fair enough, where e is the number of edges. At every level, a node receives at most these many messages. How many messages? One initiate message, right? So one initiate message to start, one accept message, one report message, right? So it receives these two. So it receives an initiate message and an accept message. So initiate and accept is what it receives every node, and it sends a report message, a change root or connect message depending upon where it is in the tree, and a successful test message. So these are the 5 kinds of messages that it sends or receives. Furthermore, there is no intersection between the sending set and the receiving set. So we can say that for every level, these are the 5 messages that every node receives. So let's say if there are n nodes, then per level we have an exchange of 5n messages right here. Alright, so you're welcome to verify this. So this is just a question of simple bookkeeping, that's all. Okay. And so I have just one more thing to add. So how many level changes will you have, right? So what happens is that anytime a level changes, anytime that a level changes, we claim that the number of nodes, it at least doubles. So I would like to make a slightly tighter claim over here. So let's go over here. So the claim that I'm making is that any fragment with level L, okay, with let's say level L, has at least two raised to power L nodes. So this is trivially true if L is equal to 0, it is trivially true. Because why? Because 2 to the power 0 is 1 and every node by itself has level 0, so this is trivially true. So now let us consider a mathematical induction based proof. So let us assume that till level L this holds, right? So basically for all levels, for all L, or let's say 0, between 0 and L, this holds. So let us now consider level L plus 1. So how do you go to level L plus 1? You go to level L plus 1 only when two such fragments combine. Alright. Otherwise you remain at the same level and then only smaller fragments come and keep on joining you, which is fine. So then this induction hypothesis will still hold. So now if let's say two fragments of the same level are combining, then this will have 2 to the power L nodes, this will have 2 raised to the power L nodes. So total will have 2 raised to the power L plus 1 nodes, right? So that is a total. So again, as we can see in the bigger fragment whose level is L plus 1, the number of nodes that it has is again at least 2 raised to the power L plus 1. So the induction hypothesis does hold. So this means that the base case holds and the induction hypothesis holds. Hence by induction, every time we increase the level, the number of nodes at least double. Alright. So this further means that with n nodes, the maximum number of levels that we are going to have is log n to the base 2. So armed with this information, let's go back. So given the fact that we will at best have log n level changes, and per level change 5n messages are sent. So the total number of messages are 5n log n. So it is basically 2e plus 5n log n is the total number of messages that we are looking at. Alright, so it is essentially 2 times the number of edges plus 5n log n, that's the number of nodes. So that's what we are looking at. So in terms of complexity, this is not that bad at all. In the sense, we are able to take a very large distributed network and create an MST with n log n message complexity, which is quite good. Alright. And in the space of distributed algorithms, of course this algorithm is complex, but now of course I hope that most of it is well understood. So now we'll discuss something called Shandy-Lamport algorithm in 1 or 2 slides. It's called a distributed snapshot. So the idea is that fine, I created a large distributed algorithm. So what? So the idea is that in a large distributed system, if let's say we have a large number of processes, debugging this entire system is difficult because they are sending so many messages, right? So let's say even if we give students a homework to implement the MST, the minimum spanning tree algorithm, so even then also, debugging it is hard. So what we do is that every process takes a local snapshot of its state. So snapshot is basically I want to capture a photograph of the entire system such that if anything is wrong with it, I can analyze the snapshot and find out what is wrong. But even taking a photograph of a distributed system where there is no clock synchrony is hard, right? So we are looking at one way of doing it. So So as I said, the algorithm is that every process takes a local snapshot. Furthermore, the process does not process any message. So of course, these are different processes. It doesn't act on any message while taking a snapshot. So what we want is, we want a consistent snapshot in the entire distributed system such that we can act on it. So what this basically means is that if there is a sender and there is a receiver, and let's say the sender sends a message, it should never be the case that the receiver is taking a snapshot of its state where it is recording the message received, but in the sender's snapshot the message send is not there. That should never be the case, right? So if let's say the receive event is there, the send event should be there. That is the only requirement for consistency. There is no other requirement per se. Alright. So if let's say that in a distributed system we were to take such kind of a snapshot, it would at least give us some kind of a photograph, which of course is not instantaneous, but might give us enough information to debug and find the source of a problem. So let's do that. So we'll use the Shandy-Lamport algorithm, which is very simple. The only assumption it makes is that we have FIFO channels. FIFO is first in first out channel, in the sense A sends a message to B, the messages are not reordered. So the algorithm is like this, that we take a local snapshot, set taken to true for each of our neighbors. Okay. We send a marker. Okay, we send a marker to each of the neighbors. So then what does that happen when a marker is received? If taken is equal to false, if a snapshot has not been taken, then then the neighbor takes a local snapshot and it sets taken to true. Again, for each of its neighbors, it sends the marker. So one thing that is clear is that, let's see, if I have a system like this, so let's say I take a snapshot, I send a marker to these three nodes. Each of these nodes then take a snapshot, and then they send a marker. Let's say the marker is sent here, here and here. But let's say this marker finds that actually this node has taken a snapshot, so the marker is ignored, right? So you take a snapshot only once when you get the marker for the first time. And after that, after the snapshot marker is done, you don't do anything and you just record the state. And that's it. Either you can stop there or you can wait for another message to ask you to resume. So that's a separate matter. We'll get into that slightly later. So the theorem 1 is the algorithm terminates in finite time. Well, why not? Because you're sending messages. Ultimately, the message will reach everybody. And since every node takes a snapshot when it receives the first marker message, it will terminate. The most important is theorem 2. That is, regardless of the distributed system, if I do this, what I'm saying is that the entire snapshot is consistent. What does the entire snapshot consist of? The entire snapshot consists of the individual snapshots of all the nodes, right? Whatever has been taken. That is what the entire snapshot consists of. And why do I say it is consistent? I claim that if a receive has been logged in the snapshot, its corresponding send has also been logged. That's my only requirement, no other requirement. So the theorem is that if a message from P to Q is sent after a local snapshot, then it is not a part of the receiver's snapshot. Fine, fair enough. So what I'm saying is that, let's say that there is node P and there is Q. So let's say it takes a local snapshot and then it sends a message. So in this case, we don't stall after taking a snapshot, but we send a message. So then what I claim is that, so in this case, the send has not been logged, right? Because I take a snapshot first and then I send, so I didn't log the send. So what I claim is that at the end of the receiver, the receive will also not be logged. And the answer is very simple. The proof is very, very simple. The proof is that when I take a snapshot, I immediately send a marker message to Q. Okay. After the marker message, I send my other message. This means that Q either gets the marker from me or from somebody else before me and takes a local snapshot, and only after that does it get the message M. By that time Q has taken its snapshot and it has not recorded the receive. Consequently, this is correct and consistent as per our definition. Given the fact that we didn't log a send, we didn't log the receive also. This was a simple definition of consistency, and as you can see, this simple algorithm does provide our definition of consistency. What is it? If a receive has been logged in the snapshot, that is, that implies the send has also been logged. So what we were actually able to prove was the contrapositive of this, that if the send has not been logged, then the receive has also not been logged, which is what we were just able to prove over here. And this is the same as this. So anything contrapositive is basically A implies B is essentially the same as not B implies not A. Alright, so this is essentially proof by contrapositive. So this is what we have done. And so we have one algorithm of at least recording a consistent snapshot in a distributed system. Why are we introducing this here? Well, the reason we are introducing this is for a simple reason, that the MST algorithm was complicated, no doubt, right? Given that the MST algorithm was complicated, when we actually code it on a system, on a distributed system, you will have many corner cases and the code is not going to work, and then this entire PQ business is going to confuse you. Furthermore, what happens, so I'll just show you one of the slides which makes our life tough actually. So it is essentially slides like these. So for example this, so where we wait. The moment we have a wait, if the code is not written correctly, you might be waiting forever, right? It might be an infinite wait. And so these wait messages are essentially what kind of make us quite jittery. Alright, so these are things that we don't like. See here also there is one more wait. So we don't like these things. So given the fact that we don't like these things, what will happen is that in most cases the code will not complete because the processes will just end up waiting because of some bug somewhere. So to debug such systems and find out what exactly has gone wrong, we can create a nice summary of all the actions that a given node has taken. We'll call it the snapshot of the node, and use the Shandy-Lamport algorithm to record a consistent snapshot, consistent as per our definition. And then this snapshot can be written to maybe the disk by all the processes. Then subsequently this can be analyzed either manually or via a script to find out what was the most likely cause of the error. That is the reason why this lecture combines a complicated algorithm with a very short and small and cute algorithm to effectively debug a distributed system, because debugging a distributed system is hard. Now coming to the references, the book by Gerard Tell has many of these details, and so there are many other distributed algorithms as well in this book, including a lot of concepts. So you are most welcome to read it and also implement the MST algorithm to get a practical feel.